the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. We talk a lot on this podcast about the importance of both encryption and privacy, but while we've touched on certain, pieces of it a little bit, we've never really gone into necessarily a full deep dive as to how some of these encryption algorithms and key management systems work, and we haven't really gotten super deep into the weeds. I mean, we've given, some of the high level, 30,000 foot view of things, right? Like we said, RSA is basically just a prime number calculation essentially, which is still true, but, it doesn't really get super in depth of how it actually works. So in this episode, I figured we'd kind of dive a little more into why it's important, and also two, kind of give some more of the behind the scenes stuff about how some of these, at least the most common kind of encryption algorithms work, and some of the key management systems as well, to hopefully kind of give you a better understanding of how these algorithms and implementations work when you implement them in your code bases. Now, I'm assuming that probably 99.9% of you don't actually write the code to do the encryption itself. At least I kind of hope you don't, because there are plenty of fantastic libraries out there. And specifically when it comes to cryptographic libraries and such, it's typically best to not write your own implementations of it, mainly because the ones that are out there that exist, I'm thinking, the OpenSSL type libraries, those are so battle tested and so rigorously verified to be, secure and basically good, that trying to roll your own, it's not to say that you can't, but it's generally not necessarily the best idea, at least when you're talking to cybersecurity researchers and whatnot, because for instance, if you write an implementation and say your implementation has a bug in it, but you don't know it has a bug in it, well, it's on you to fix it. And if you don't know that there's a bug in it, well, you might have a hole in your encryption, and threat actors can take advantage of that. Whereas if you use something like OpenSSL and there was a bug in it, for instance, that would obviously get noticed a lot quicker, patched, and you would take advantage of those updates. So unless you're working on one of those encryption libraries, you're probably not rolling your own. But regardless, it's still important to understand how these encryption algorithms and key management systems work, just to kind of give you an understanding of what you're actually implementing. Also, on a completely unrelated note to this podcast, can we just have a brief moment of silence to everybody's stock and investment portfolios? Because it's been absolutely brutal this past week. If you have no idea what I'm talking about, I think everyone that knows what I'm talking about envies you at this moment. But what I will say is, if you don't know what I'm talking about, don't do yourself a favor and don't look at your investment accounts, because the markets as a whole have basically dropped 10 to 12% this past week, and some standalone companies dropping more than that. So big, I guess, as the kids say, F in the chat. Moment of silence for people's portfolios. But with that, let's get into this week's trivia question, which, in the theme of encryption, AES, or the Advanced Encryption Standard, is a specification for the encryption of electronic data established by the United States National Institute of Standards and Technology, or NIST, in what year? So what year was AES established? And that is your trivia question for the week. Now, speaking of the whole data management and data privacy, you guys remember, I don't remember how long ago it was when there was that story about 23andMe and how they had that massive data breach and a bunch of people's like DNA info got leaked. Well, last week they filed for bankruptcy and are looking for a buyer. So the lulls just keep on lolling. And the reason why I guess this matters is because 23andMe, if you are, I guess, living under a rock, they deal with people's DNA information, their DNA, genome sequence, whatever it is. Um, and they have that information for who knows how many people, probably somewhere in the millions. Not sure if it's tens or hundreds, but they probably have lots of people's personal data. And even going based off of that, even if they don't have everyone's, they can get a pretty good sense of people that are related. So, for instance, if you didn't use 23andMe, but say your sister or your brother did, they're probably able to get a pretty good sense of your DNA makeup just based off your relatives. But anyway, people are basically freaking out about this because they're like, oh no, what's going to happen to my data? Which, props to you for caring about what's going to happen to your data. I definitely commend that sentiment. But at the same time, what did you think was happening when you initially freely gave all that data to 23andMe? Now, of course, people are worried that some, data harvesting company is going to try to buy up 23andMe, get a hold of all this data, and do potentially nefarious things with it. For instance, you could imagine if an insurance company gets their hands on this. Now, while technically speaking, by law, insurance companies, I don't believe, are allowed to deny people coverage due to pre-existing conditions. But if they see in your genome that you happen to have a certain gene that might make you, maybe you don't have something, but some gene might mean you're a potential candidate to have something in the future, I don't know. I'm sure there's some legalese that they can try to spin to make it seem like they're not discriminating based on that. But in reality, again, you can't prove a negative. But yeah. So anyway, people are freaking out about this. But at the same time, so 23andMe, they did they claim anyway that you can delete your account and request that your DNA sample be discarded as well, and all of that should be deleted within 30 days or so. Now, if you're a company that's looking to buy 23andMe, theoretically, you're buying them for the data that they have. So all of the people that are kind of I guess not spam, but flooding 23andMe to delete their accounts and have all their data removed, technically from 23andMe's perspective, that's just lowering the overall value of what a company would be willing to pay for them. So would they be willing to basically throw all that money away and basically drive down what their value is down? Now, you can make your assumption as what you think would be their kind of MO there, but also, I guess we should also mention that there's really no way for you to actually verify that any of your data actually gets deleted, because it's not like 23andMe are letting you go into their data farms, wherever they are, their server farms, and manually inspect all of their servers to make sure that all of your data is gone. They're, of course, not letting you do that, so you basically have to take them by the Trust Me Bro guarantee. Now, maybe I, of course, don't have a 23andMe account. Maybe there's some legal jargon holding them responsible when you do delete your account that they say, and they will be legally held liable or something if they don't delete it. I don't know. But the point is, if you think about it, it's kind of going against their best interest to basically remove all these people's data that want their data removed, because it basically just lowers their overall value to a would-be buyer. So yeah, I get why people are outraged, because again, you have no idea who the potential buyer would be and what they would potentially do with all of this data. But at the same time, you also kind of willingly gave all of this data to a company in the first place. So, and 23andMe has also used all this data to perform various research and other who knows what. So it's not like your data was always just kind of sitting there and no one was touching it in the first place. But yeah, very interesting situation to be sure. Now, I will have kind of a link to more of the information on their bankruptcy and whatnot down in the show notes if you're interested in taking a look. And with that, let's move into this week's cybersecurity tip. This week's cybersecurity tip is to basically be careful of iMessage and RCS, in the sense that not every message that comes over those channels is legitimate. And I bring this up because there was a recent report done by 9to5Mac, which I will have also linked in the show notes, that basically they report that there are massive farms of iPhones out there that are basically sending scam messages via iMessage. And the reason why this is so effective is basically because iMessage is end-to-end encrypted. Because one of the ways that cell phone carriers are able to block spam text messages is because typically all those messages are sent in SMS, which is just plain text. And because of that, the phone carriers are able to use various filters and whatnot to detect the data inside those text messages and to be able to identify spam. But of course, if the data is being sent through the internet via iMessage and it is all end-to-end encrypted, there's really nothing anybody can do, because to anyone trying to monitor the traffic, it's just a bunch of garbage anyway. So this is kind of the, I guess, double-edged sword, if you will, to end-to-end encryption. It's fantastic for things like preventing would-be threat actors or nosy governments or whatever from seeing what you're doing. But at the same time, it's harder from kind of a, I guess, a mass scale level to block things like spam. But you can implement things like on your device itself that you could make your own spam filters. I guess kind of the only caveat to that is you kind of have to put your trust in whatever your filter is. So for instance, if you're on an iPhone and you download some app from the App Store to basically further filter your messages to kind of remove some of this spam stuff, you basically have to give access to your messages to that app, which you may or may not want to do, because everything's end-to-end encrypted, the app itself has to have access to all of your iMessages in order to be able to, actually see what they are and see if they're spam or not. So that is kind of one thing you have to keep in mind. But anyway, some of the spam things that are being, I guess, perpetrated by these threat actors include things like unpaid toll fees, claims that shipping fees are needed in order to release valuable packages from customs, and then kind of like fictitious warnings about unpaid taxes. Now, personally, I'm pretty sure I've received some of these. Like, I'm pretty sure I got at least the tolls one, but I think I got the tolls one at least 2 or 3 times, maybe, I think. Not sure about I think the customs one, maybe I've gotten that one. I don't think I've gotten the taxes one. But it is really weird because you see like this iMessage come through and you're like, huh? That's weird. But I think it's important to note, and we should remember that none of these issues would be resolved via any kind of messaging service like a text message, an iMessage, or RCS, or anything like that. Especially the taxes one and probably the tolls one too, because I'm pretty sure basically any toll like company or whatever, like if you drive on a toll road and you don't pay your toll, they're just going to send you a bill in the mail based on your license plate. They're going to do a lookup of your license plate, figure out where you live, and basically send the bill there. And the same thing with taxes. Like the IRS doesn't send you text messages being like, hey, you haven't paid your taxes yet, which, by the way, if you are in the US, April 15th is coming up pretty quickly. So if you haven't done your taxes, here's a friendly reminder. But they don't send you text messages letting you know that you have unpaid taxes. So just one thing to kind of remember there. But also, the other thing to remember too is, without a doubt, when it comes to anything you're unsure of, or even just anything in general, if you ever get the best foolproof way to basically not get yourself hacked by someone sending you any kind of message is to never click on any links, because if you don't click on any of the links, you can't get sent to some malicious website trying to steal your information. So, the most common example is like a threat actor sends you a fake link to what looks like your bank account. If you click the link, this website looks exactly like your bank account. The only difference is if you look at the URL is obviously different. But basically what happens is the point of them is to make the website look exactly like the real deal, to fool people to enter in their credentials, in which case they basically goes into their back end rather than logging you into whatever you're trying to log into, and thus they steal your credentials. So remember, when it comes to anything dealing with someone trying to get you to do anything actionable, there's two things you first need to check. First, you need to check who is actually sending this message. Is this an actual reputable sender of the message? So for instance, if it's coming from your bank, I guess in this case, iMessage, which your bank wouldn't send you an iMessage like that. So that would be red flag number one. But the other thing would be to actually verify that the phone number that's being sent from is actually from your bank, which it probably isn't if it's sending an iMessage. The second thing is to verify the link. Now, you do have to be careful with the links, though, because it is possible to basically hyperlink something but not have the text match up with the actual link it's pointing to. So you do have to kind of inspect that a little bit closer before you just blindly click on the link. But again, the most foolproof solution is if you see a message, again, we'll just use the bank since we're kind of been on that track. If you see a suspicious text message, email, whatever that looks legitimate from your bank about some issue with your account, don't click anything in the message. Just go directly to your web browser, type in the exact address of your bank, go directly to your bank's website, log in manually, and if there truly is an issue with your account, there should be something very noticeable as soon as you log in telling you that something is up. Or if it's not immediately visible, there should be somewhere where there's kind of like a notification type center, and it should be visible there. So those are basically the ways that you can kind of help prevent yourself from getting hacked. So yeah, definitely kind of interesting to see this happening with iMessage, and supposedly RCS too. So definitely something that you all should be on the lookout for. And that is your cybersecurity tip for the week. Before we get into the nerdy things, I did want to touch on one more quick news story, which is the supposed TikTok ban 2.0. Now, if you'll remember, back in January, TikTok was supposed to be banned because of the quote-unquote ban TikTok bill, which, as we've covered on the podcast, is not a ban TikTok bill, but if you want to hear more, you can go listen to one of those previous episodes. But anyway, the ban was basically kicked down the road 75 days, and wouldn't you know it, this podcast goes live on April 5th, which also happens to be 75 days after, or basically the 75-day deadline. So theoretically, the day this podcast goes live, TikTok gets banned again unless someone buys it. I don't know. You guys probably would have more information than I do as of recording. So for all I know, this recording, might be just way off. So my apologies, unless there's basically some kind of like last minute Hail Mary going on. It doesn't look like there currently is a deal in place for TikTok to be bought. Now, with that said, there are numerous American companies and whatnot that have put in bids to purchase TikTok, including Frank McCourt, the former Dodgers owner, and a Reddit co-founder, Alexis. I don't know how to pronounce his last name. Kevin O'Leary, one of the Shark Tank guys. A company called AppLovin, Perplexity AI, and basically at the very last second, I think even Amazon kind of threw their hat in the ring with a bid. And there's also rumors about like others potentially buying it, like Mr. Beast, which that would be absolutely hilarious, and even Oracle. And I think the reason why Oracle is supposedly in the mix too is because my understanding is Oracle is like the platform that TikTok uses to kind of host their services in the US. At least that's my understanding. Now, Vice President J.D. Vance said basically on the fact of will there be a deal by April 5th, he said, quote, "There will almost certainly be a high-level agreement that I think satisfies our national security concerns and allows there to be a distinct American TikTok enterprise." I guess take that what you will if there will be a high-level agreement. Although Trump has also made his own comments about possibly kicking the can even further down the road and further delaying the deadline, or even telling his Justice Department not to enforce the ban, which basically means that App Store maintainers like Apple and Google, and I guess Oracle, since they're supposedly the hosters of the TikTok site, wouldn't have to actually take them down and they could leave them up. I don't know. I guess we'll see what happens. But like I said, you got tomorrow, or I'm recording this on April 4th. Tomorrow or April 5th is the deadline, which is when this podcast goes out. So you probably know more than I do. So yeah, it should be interesting. But with that, let's get into what nerdy stuff have I been up to this week. So pretty light on the nerdy things, but just kind of real quick. So I mentioned a while back, like a few months ago, how I wrote a couple of, basically a collection of scripts to basically build my own Linux distro from scratch. And one of the kind of outstanding things with that was I wanted some kind of way to verify all the dependencies were installed to basically fully make it cohesive, to make it that you could basically just run this and get the Linux distro, right? And my solution was to use a Docker file to basically create a Docker container, build a Docker environment, and basically have a fully controlled ecosystem where I could make sure all the dependencies are installed, build everything, and then I can extract the ISO from the built container. That didn't exactly go according to plan. Now, as we'll get into later, starting off with the Docker file was definitely not the smart move. So the short version is it failed. The long version is when I got to compiling GCC, for whatever reason, it was complaining that some directory wasn't existing that I think was somehow related to GCC. I'm not entirely sure. I haven't really had a ton of time to comb through the multiple megabytes worth of logs that this build process spits out. But like I kind of alluded to, I realized that this was a very, very dumb idea, because when I was originally building the script, I was kind of doing it very iteratively, in the sense that I was, making sure I got, the Linux kernel building properly, then adding the next package like BusyBox, making sure that builds properly, then GCC, then glibc, and basically all the components, making sure they all build correctly, and then kind of running the entire script to make sure the whole thing works. Now, I was not being a good developer when I was creating this script because I was not keeping track of the dependencies that were required in order to build all the various components. So that was kind of issue number one, where I kind of had to kind of walk back through and kind of figure out retroactively all the dependencies that I needed. But the other thing that is very annoying about trying to build in a Docker container is you basically start from zero every single time. Now, it's good in the sense that you can always guarantee you get the same output every time. But when you're doing something as time and compute intensive as building a Linux distribution from scratch, it's not very optimal for making sure and testing minor tweaks and changes, because in my case it was taking about like 20 minutes before the thing would fail. And I guess to take a little bit of a step back, what I should do, and I think what my plan is going forward, will be to create a VM that I can take snapshots of, and then basically kind of do the same iterative process like I did when I was first creating the script, and basically ensure that I can track and identify all the dependencies that I need and iron out any kind of issues within the VM, kind of doing it iteratively, so I don't have to wait like 20 minutes just to realize, oh yeah, the change I just tried to make didn't work, because that's really not a good use of my time. And the reason why it took about like 20 minutes or so is because I was running this on my Docker virtual machine that I have running on my R620. And the Docker virtual machine only has 8 E5 2695 V2 CPUs assigned to it. So obviously it's not like it doesn't have necessarily a ton of resources assigned to it, and these CPUs are kind of quite old at this point. But even with that, 8 out of the 48 total cores, or about like 17% of the CPU, since the R620 has 2 CPUs installed. The fans were still going at a pretty good clip there. They weren't like screaming like an Xserve, but they were fairly loud. And so yeah, it needs more work. But like I said, I think my next plan going forward to kind of get this working is the inevitable end goal is to have it working in a Docker container. But I think in order to get there, I'm going to put it in a VM first, kind of iterate through, make sure everything kind of works. I can get it working all the way through, and then kind of transfer that knowledge over to the Docker container. Because at this point, I know the script works because it's built working ISOs for me before. It's mainly at this point, it's just a matter of making sure I have everything in a fresh environment, rather than kind of a dev environment that I was kind of haphazardly adding and removing things, and tweaking the settings of things to, while I was building out the script. So starting from fresh, working through everything, documenting everything, and I think that's going to be what I do going forward. So now let's get into this fun world of encryption. So first, I kind of want to paint a picture for you of why encryption is so important. So let's say, hypothetically speaking, you are a loyal customer of an online retailer, and you recently placed an order, and you entered, all your information, your name, your address, credit card details, all that good stuff, got the confirmation email, everything's good, your order's shipping, and then a few days later, you get a notification that your account has been compromised, and you now see a bunch of bogus transactions on your credit card for various unauthorized purchases, and your personal information has been sold on the dark web. Now, while this is technically a hypothetical scenario, as you all are probably well aware, this happens far too often in the real world. And this is why there is such a need for data protection out there, because it's not necessarily specifically all about compliance and whatnot. And, from the business aspect, customer trust and all that. the thing that you have to keep in mind is when it comes to encryption, there's really two components of it when talking about data protection. So the first one is you have your data at rest, which basically when the data is stored on servers and databases on your personal devices, etc., it being encrypted there. So if someone tries to get physical access to the system, the data is encrypted, or if they try to hack into it and they try to, get a leak from a database, if all the information in the database is encrypted, they just get a bunch of encrypted garbage and they can't really do anything with it. Whereas if it's not encrypted, then they just get plain text of everything and they can basically go have a field day. And then the other component is encryption in transit, which is kind of, while data is moving across networks, whether that's internally or over the internet, having the data encrypted. And this is kind of where the whole idea of end-to-end encryption comes in, which we've talked about quite a bit on this podcast. If we kind of revisit the whole Target example that we talked about a few weeks ago, the Target breach that happened back in 2013, where basically 40 million credit cards and debit cards were stolen, which kind of led to lots of financial loss for customers. It poses the question of, could encryption have prevented this? And the short answer is yes. So the breach wasn't caused, as we kind of touched on, wasn't caused by a sophisticated hacking. It was basically a vulnerability in Target's point of sale systems. But if the data was actually encrypted at rest and stored, say, on Target server somewhere, if the attackers still managed to get in and say they managed to get access to whatever database Target stored all this information in, if they got access to the database and were able to dump it, if all the data was encrypted, yeah, they would have stolen the data, which would have been, obviously not good for Target, from the optics of things. But because everything's encrypted, the threat actors would basically have nothing to go off of, it just be a bunch of gibberish. So this is one of the key reasons why encrypting your data at rest is so important. So when it comes to encryption, there's really two kinds. You have, as we've touched on in the past. So you have of course your symmetric encryption, basically your symmetric key encryption, which is basically kind of a lock and key, right? So you have one lock, or you have a lock, and you have a single key that both locks and unlocks the lock. So if you kind of think of this like the key to your house, right? You can give someone the key to your house, and it's basically the exact same key as you have. But the downside of the one key solution here is if either you lose your key or the key you gave to someone else falls into someone else's hands, that person now has the ability to get inside your house. Just like with symmetric key encryption, you can give the key to whoever you want, but if that key happens to accidentally fall into a threat actor's hands, they can now get in and decrypt all of your data, which obviously isn't good. Now, when it comes to symmetric key encryption, the gold standard, I guess, kind of today is the AES, or the Advanced Encryption Standard. And it's one of the most widely used symmetric key encryption schemes out there. So AES works on a block cipher kind of method for its encryption, which we'll kind of get into a little bit more about how that actually works. But basically what this means is it encrypts data in chunks or blocks, typically about 128 bits in length. And it basically uses a series of mathematical operations, substitutions, permutations, basically a bunch of different ways to transform and jumble the data. So it's basically you're unable to get anything out of it unless, of course, you have the key. Now, the key lengths for AES are typically either 128, 192, or 256 bits in length. So kind of a quick overview about how this actually works. So first you have kind of the key expansion portion, which is where the round of keys are derived from the cipher key using how AES actually schedules and requires. So AES basically requires that a separate 128-bit round key block be used for each round. So basically this kind of adds more randomness to it. So you're not, because one of the kind of issues, if you kind of delved into some of these kind of like block type ciphers, there's a couple different ways you can do block ciphers. One of them is if you always do it the exact same way every time. Um, one of the issues is like if you decrypt part of it, you can kind of get a sense of what's actually going on there. So one of the great ways to actually visualize this is if you encrypt like images. In theory, if you do it properly, you just get a bunch of noise. But depending on which kind of like block kind of cipher you use, you basically can still make out what the image is supposed to be. Like, it's obviously not clear, but you can visibly see like the different blocks of chunks, like where things kind of got jumbled, but it's very kind of uniform in that sense. So you can still kind of sort of make out what it's supposed to be. So anyway, going back to AES here. So AES basically does multiple rounds of this encryption to kind of like go over and really jumble things up, typically somewhere between 9, 11, or 13 rounds. And basically each kind of round through this, there's a bitwise XOR operation that happens. So if you're not familiar with the XOR operation, basically what that is if you look at the truth table for it, if you have a 0 and a 0, you get a 0. If you have a 1 and a 0, you get a 1. If you have a 0 and a 1, you get a 0. And then if you have two 1s, you get a 0. So you only get a 1 if there is 1 1 but not 2. And of course, if there's a 0, you obviously get 0. So bitwise exclusive ORs are very common in the world of cryptography. So then kind of after you do that, you get into the sub-bytes, which is kind of a substitution step where each byte is replaced with another according to a lookup table that's kind of within AES. And then you kind of like shift the rows, which is the transposition step, where the last 3 rows of the state are shifted cyclically to a certain number of steps. So basically kind of like as we touched on, you're really just kind of like trying to jumble this data around to really kind of mix things up. And then you just kind of keep cycling and repeating till you end up with like 10, 12, or 14 rounds in total and really mixing up this data. So AES, one of the kind of the gold standards when it comes to symmetric key encryption. Then we get into asymmetric encryption, which is also known as like public key cryptography. So the concept here, I guess from kind of like an abstract view, is you can kind of think of this. So of course you have your public and your private keys. So kind of the analogy here is if you know, might be dating myself, but if you remember those kind of those blue mailboxes like the post office would have, like kind of around towns and whatnot, anyone can put mail in them, but only the post office can actually unlock the mailbox and actually get the mail out to then go and kind of deliver it. So that's kind of what the public-private key encryption scheme is. Everyone can have your public key, but only you can have your private key, at least if you want your data to be secure anyway. Now, when it comes to asymmetric encryption schemes, of course, RSA is kind of probably the most famous, although it's with the whole quantum computing thing and Shor's algorithm, it's not quantum resistant, so people have been trying to come up with more quantum resistant algorithms. But RSA is definitely one of the oldest and kind of most established public-private key crypto systems, and it's basically been used for decades at this point. So kind of as we've touched on with RSA when we've talked about it in the past, RSA relies on the mathematical difficulty of factoring large numbers together into their prime factors. So basically it uses the public key for encryption and the private key for decryption. So basically the way this works is anyone can encrypt something with your private key and send it to you, and then only you are able to decrypt it with your private key. So you can... So basically, if someone wants to if you want to do kind of a kind of a verification of who sent you the message, if Bob and Alice, they both have each other's public keys, basically what can happen is Alice can basically encrypt the message with Bob's public key, so only Bob can decrypt it, and then she can kind of use her private key to basically kind of add a signature to it in a sense, so then her public key can kind of verify that it was her private key that kind of signed it, so Bob can know that Alice was the one that sent the message, and then of course he can use his private key to decrypt it. So basically kind of how it works is the public key is derived from the product of two large prime numbers, and then the private key is derived from the original prime number. And then the encryption process involves raising the plain text to the power modulo of the private key, the public key. And modulo is basically a way of saying, so if you take any number to say module 2, since modulo 2 is kind of the most basic example, 1 modulo 2 is obviously 1, 2 modulo 2 is 0 because 2 is divisible by 2, 3 modulo 2 is 1 because 3 divided by 2 has a remainder of 1, and then 4 modulo 2 is 2 because 4 obviously divides evenly into 2, and then kind of so on. So that's kind of what the modulo operator is. It's basically just the remainder. So then the decryption process involves raising the ciphertext to the same power modulo with the private key. So the strengths of RSA is it's very well understood. It's very secure when dealing with classical computing. Once you kind of get into the quantum realm, that's kind of a different story. But very widely used for things like digital signatures, kind of that Bob and Alice example we touched on. You can use them to basically digitally sign data to basically verify that you were the one that sent it by using your private key. Use things for like secure web traffic like HTTPS. Now, of course, the weaknesses, as we've touched on and alluded to a couple of times, is RSA relies on the difficulty of factoring large numbers. Now, while this is good for, classical kind of computing, it falls apart when you get into the quantum realm. And even if you have large enough GPUs can... Of course, with the number and scale of what we're talking about with RSA keys, GPUs are still probably not going to do the trick, but I even wrote a program, a CUDA program that runs on NVIDIA GPUs to basically show this in action. Now, granted, it's obviously not the real deal. It's mainly just a proof of concept. But kind of the thing is because even the CPU is able to crack the prime factors within a matter of I don't remember what it was. I think it was 2 seconds or something like that. It's fairly, maybe it was more than 2 seconds. I don't know. It's still cracked it in a fairly reasonable time, but the GPU basically did it instantly. So, but granted, these were only 64-bit numbers and RSA keys are significantly larger than that. But the problem with RSA is because it relies on these prime number factorizations, it's already been proven not to be quantum resistant thanks to Shor's algorithm. Now, we're not going to go into all of what Shor's algorithm is, but suffice it to say, Shor's algorithm is an algorithm that basically can crack RSA when run on a quantum computer. Now, as it stands right now, quantum computing isn't at the point where it can trivially crack RSA like that, so you don't really necessarily have to worry about it. But there will eventually come a point in quantum computing where Shor's algorithm will be able to crack RSA keys like you crack eggs for breakfast. But thankfully, we aren't quite there yet, but it definitely is in the future. Now, another kind of the more modern version of RSA is what's known as ECC, not to be confused with the ECC that stands for error correction code, the memory type, but elliptic curve cryptography. So ECC is a newer type of cryptography that has been definitely gaining significant traction over the recent years, and probably even over 5, maybe close to 10 years at this point. It's been around a little bit, but it's definitely significantly newer, especially when compared to RSA. And it offers comparable security to RSA, but the benefit here is the keys are significantly smaller and it's also more efficient, which is very beneficial for much smaller devices with limited resources like IoT devices or other, kind of embedded type systems. So the key idea with ECC is it's based on the mathematical properties of elliptic curves, specifically the way points on elliptic curves behave when you perform certain calculations on them. So it's basically... it's based on the difficulty of elliptic curve discrete the logarithmic problem. Now, we're not going to go into all of the math behind that because, quite honestly, that's probably goes above my head. Get yourself a mathematician to do that. But essentially, it kind of like I said, there's this logarithmic problem with elliptic curves that is basically very secure. So it's kind of a different approach from RSA, which RSA is like, hey, let's just take, big numbers and find the prime factors of them. So because it's a discrete logarithmic problem on an elliptic curve, ECC relies on the fact that it's extremely, very, very, very difficult to figure out the private key from the public key because of how this calculation is performed. So it's kind of just some context for you. And like I said, because I don't fully understand it, I don't want to go into all the weeds of specifically how that works, because I'm sure I'd probably lose a lot of people trying to explain it anyway. But if you're interested, I'm sure you can find plenty of resources that go way more into the weeds than you would probably ever care to know about ECC. But kind of getting back to the strengths of it, kind of as we touched on, the key size is significantly smaller. So ECC, for context, because context is always very important, we like to give context on this podcast, ECC offers the same level of security as RSA, but like I said, with significantly smaller keys. So a 256-bit ECC key provides the equivalent level of security as a 3072-bit RSA key. So significantly smaller, and because it's significantly smaller, like we said, it's a lot more efficient, which is fantastic for things like embedded devices and IoT devices, which are obviously have significantly less resources and less power allocated to them to perform, these cryptographic operations. And ECC, while it might be newer, it's still gaining, more widespread adoption in things like mobile payment systems, secure messaging apps, blockchain technologies, and the like. So kind of to kind of recap here, when you're comparing RSA versus ECC, RSA has significantly larger keys compared to ECC. RSA has its mathical basis on factoring large numbers, where ECC is the elliptic curve discrete logarithmic algorithm. RSA is not nearly as efficient as ECC is. ECC is significantly more efficient. RSA has its primary uses in things like HTTPS, digital signatures, and that kind of a thing. And ECC currently is kind of more in like mobile payments, blockchains, that kind of a thing. So all this encryption stuff is cool and all, but specifically for the asymmetric keys, it doesn't matter who you give your public key to. But for symmetric key encryption, you could have the most secure symmetric key encryption algorithm in the world, but if you want to share information with someone, how in the world do you securely get your key to them? And that is where things like key exchange mechanisms come into play. So one of the most common is the Diffie-Hellman key exchange mechanisms. Now, Diffie-Hellman solves the problem by using also mathematical properties, specifically the modular arithmetic. So this key exchange protocol basically creates a shared secret without transmitting the secret itself. So we're going to kind of get into an example of how that works. And of course, we're going to be using security's favorite duo of Bob and Alice, trying to share keys with one another while Eve is trying to steal from them. So I guess to set the stage here, of course, Bob and Alice, one of them has a key that they want a symmetric key that they want to share with the other one. Now, to demonstrate how this works, let's actually walk through a basic example. Now, for the sake of this example, I'm going to keep these numbers small just to make kind of the math easier, to make it easier for you to wrap your heads around. But basically how this works is Bob and Alice start out with a public prime number and a generator. So the prime number for our example will be 13, and the generator will be 6. Now, like I said, these are publicly known, so in our case, they cannot be intercepted by Eve because, like I said, they're public knowledge. So Alice selects a random number for her private key. So say she selects 18. This will be A, little a for Alice. And then Bob selects his private key, or little b, and for this example, let's say he picks 8. Now, of course, Eve doesn't know what Alice's value is or what Bob's value is, so how they kind of encrypt this, if you will, is they take their secret number and they basically take it to the power. So they take G, so in our case 6, to the power of the number they selected. So for Alice, that would be G to the power of little a mod P, which comes out to be 6 to the power of 18 modulo 13. And remember, the modulo operator is basically just the remainder value, and that equals 12. So she then sends 12 over to Bob, and this will be big A. And then Bob does the exact same thing, but with his little b, his private value. So Bob calculates G to the power of B modulo P, which comes out to be 6 to the power of 8 modulo 13, which equals 3. And then he sends that to Alice as big B, or his public key, if you will. So in order to compute this shared secret between each other, Bob and Alice now have to have each other's public keys, which we have as big B for Bob's public key and big A for Alice's public key. So in order to get the secret, they basically take the public key to the power of their private value modulo the prime number. So for Alice, she computes the shared secret as big B to the power of A modulo P, which comes out to be 3 to the power of 18 modulo 13. And Bob similarly computes the secret as big A, or Alice's public key, with his private to the power of his private value B modulo P, which comes out to be 12 to the power of 8 modulo 13. And if you do the math of both of those expressions, both of those values come out to be 1, so then 1 is their secret value that they can then use to encrypt the symmetric key that they can then send to the other one, and Eve will basically have no idea what it is because she doesn't have the shared secret key. Now, you might be thinking, well, couldn't she just reverse engineer what the private numbers that Bob and Alice used were? Because everything here is public knowledge. The prime number is public knowledge, the generator is public knowledge, the public key for both Bob and Alice is public knowledge. You know the formula used to calculate the public key, so why don't you just keep plugging in numbers until you get the value that gives you the correct result, the correct public key? And it turns out that when you're actually using the numbers large enough that are typically used with Diffie-Hellman, this is computationally infeasible. Now, of course, with our small example that we did here, it is very trivial to perform the calculations to figure out which numbers gave you Bob's public key of 3 and Alice's public key of 12, and then based on that private value, you can then easily create the secret key that they then share amongst each other. And also, because these numbers are so small, there are tons of conflict values. So even if you didn't pick, Bob's 8 and you picked another number, I don't remember offhand, another number that worked, I think maybe like 20, like you don't even have to pick the same private number that he did, and you can still get to the same answer and get to the same shared private key. But again, because the numbers in Diffie-Hellman that are typically used are so much larger, this is actually computationally infeasible. So it's also worth noting here that, of course, this only matters for symmetric key encryption, as we touched on, because for public and private keys, it doesn't matter who gets your public key, so you can basically send that out into the ether unencrypted, and it doesn't matter if a man in the middle gets a hold of it, because again, the private key and public key, you can't use the public key to decrypt something that the public key encrypted. So why does this math work? So the magic basically lies in that modulo operator. And as we touched on, the modulo operator is basically just taking the remainder. So because that G, that generator value, is being raised to different powers modulo the prime number, it basically creates unique sets of values. So the fact that you can take G to the power of some value modulo P, as well as G to a different value to that same modulo P, and you get the same result, demonstrates that A is equal to B, and you basically get the shared, or basically can allow you to determine the same shared secret because of how this modulo operator works. It's also important to note that neither Alice nor Bob are revealing what their actual a and little b values are, but they're able to determine that shared secret because of this mathematical operation that's going on. So one way you can kind of think of Diffie-Hellman in kind of a abstracting away from the computer science and math is think of it like mixing paint. So Alice and Bob each have a different color, but by combining them in a specific way, they can create the same shade and thus a shared secret. Without actually having to know what the other person's color was that they initially chose. Now, of course, Diffie-Hellman does have some limitations. There is a specific vulnerability with it where a certain man-in-the-middle attack could occur. Basically, what happens is the man in the middle will basically take Bob's value and take Alice's value, so they have a copy of, so in this case Eve, so Eve takes Alice's computed value and Bob's computed value and basically sends them her computed value, so then she can then basically do some manipulation to kind of see what's going on in between there. But one of the trivial ways that this is kind of mitigated against is using Diffie-Hellman in conjunction with other authentication methods like digital signatures and certificates and things like that. So basically, Alice, when she sends her public key value over to Bob with Diffie-Hellman, she signs it with, say, her private key. So that way, even if Eve does intercept it and tries to send her own value to Bob, Bob can tell that that value is not signed by Alice, in which case he knows that it's not legitimate and there's someone in the middle. So those are some of the ways that Diffie-Hellman is used in conjunction with other kind of encryption methodologies. So then once you have your keys, you have to have some way to manage them effectively. Because just like passwords, if your keys get leaked, well, you're kind of toast then, right? So like if you let your SSH keys get out into the ether, anyone that gets a hold of them can now log into your devices and services impersonating you. Or if they get access to your private keys, they can basically impersonate you because theoretically only you should have your private key. So this person sent a message with your private key, signed by your private key, therefore that must be you. So having a strong way to store your keys is definitely important. And key generation is basically the kind of the foundation of the secure system, but kind of like if a weak lock is easily broken, you kind of need to make sure that you have a way to protect it. Otherwise, kind of like the whole system falls apart. So when it comes to kind of like the generating some of these strong keys, one of the things that often comes down to is some form of random number generator. Now, typically when we talk about random number generators in the computer science world, we talk about pseudo random number generators. Now, while pseudo random number generators might seem random, they are in fact not, and they are actually just some mathematical operation going on based off of some initial seed value. And the problem with them is if you know what that initial seed value is, you can easily compute exactly what the next random number in the sequence is going to be. And if that's what you're basing your encryption off of, well, your encryption is kind of shot. So we need something more akin to true randomness, and this is where entropy sources come into play. Now, entropy, when it comes to random number generation, is basically using unpredictable data for the seed for the randomness. So rather than maybe the system clock, which is a very predictable number as your seed value, you use some other form of unpredictable data for your seed value. So this can come through a various array of sources in regards to entropy sources. It can come from specific hardware random number generators. Now, these are by far the most secure and basically tapping into physical phenomena, things like thermal or noise, or maybe if you're fancy and in some kind of lab environment, maybe you have some kind of radioactive elements or something, or some other, maybe like a sound source. Maybe you have a speaker that kind of like taps into like the background noise of the room, and then based off like the noise, it can like generate some entropy source. You also have operating system entropy pools. So some operating systems can collect various entropy sources, say from like keyboard presses or mouse movements or network activity, and base their entropy off those sources to provide some kind of randomness source. And then kind of dedicated entropy collectors, so like kind of some kind of specialized hardware basically to generate this random entropy source from. So when it comes to anything cryptography related, you always want to make sure that when you're using random number generators, using secure random number generators, that means you're using some kind of random number generator that has some other entropy source that isn't, your standard like clock-based or otherwise pseudo-random number generator predictable random number. Because when it comes to cryptography, if you're generating keys, of course, like we touched on, you need to make sure that those can't be easily reverse engineered by knowing what the seed value is. So that's why entropy is so important. But the other portion, too, as we kind of touched on, is the whole key management portion. Nowadays, I think probably one of the most common ones, especially on like consumer devices, is hardware security modules. So these are essentially dedicated hardware devices specifically designed to securely store and manage cryptographic keys. And they basically provide a trusted hardware environment for isolating the keys from the rest of the operating system and application space. And basically this significantly reduces the risk of compromise of your keys, which is obviously very important. And of course, if you hear kind of this idea of a hardware security module and it sounds familiar, this is basically where your TPM or your trusted platform module, like on PCs, comes in, or in like the Apple space, that would be like your secure enclave, like a specific hardware device to secure those keys. So basically how they work is they operate on a kind of a tamper resistance mode. So basically if someone tries to physically access the keys themselves and kind of like physically tamper with the module, it'll basically destroy the key. So basically like, oh, you want to gain access to this and you don't have permission to? Well, too bad. We're just going to get rid of it so you can't access it. So one of the big uses for this is obviously high security applications, things like digital certificates, payment processing, key management of critical infrastructure, things like that. So things that you could potentially store in here, things like your private keys for your digital certificates, maybe SSH keys, things like that. And then you also have, your more of your software-based key vaults too. This has kind of been kind of more, I guess, more kind of cloud focused. So when you're kind of in a cloud computing environment, obviously in most cloud computing environments, you don't typically have a dedicated hardware with these kind of hardware security modules on them. So you have to have some other kind of solution for them. Most cloud providers offer some sort of means for doing this. Amazon has their AWS key management system. Microsoft has their Azure Key Vault. Google has their cloud key management system. And all of them basically offer various features from like key rotation, access control through like IAM policies, auditing, integration with other cloud services, that kind of a thing. And one thing I kind of touched on there that's important is key rotation. And key rotation is kind of like changing your passwords, because while keys generally are more secure than just kind of like your typical password, because it's a lot harder to crack a key, if your key does get leaked, you kind of need to make sure you change your key. So one of the kind of benefits of rotating your keys around is you do kind of prevent the potential for, say, your key getting leaked somehow. So if you do, say, rotate your keys on some kind of recurring basis, even if your key did get leaked, maybe that was the key you used like 2 or 3 keys ago. So if a threat actor did get a hold of it, they couldn't get into anything because you've already changed your keys at this point. So the regular rotation, periodically changing your keys that you use for encryption and decryption can potentially mitigate the impact of a threat actor kind of gaining access or compromising a key if you're constantly rotating them they only have a limited amount of time to, gain access to your stuff, assuming you didn't know that the key was leaked. So one thing that'd be kind of beneficial to this, if you do have some way to manage your keys, is to have some kind of automation set up to kind of rotate the keys effectively. Because obviously, and this is kind of one of the benefits of the cloud, is you can kind of do all that automatically. It kind of automates it for you, because having to basically go in and manually change the authentication with all of your various accounts to your new keys would be very tedious, time consuming, and quite annoying, which is probably why a lot of people don't really tend to change their passwords, because it's kind of annoying to have to go in and change your password if you don't necessarily need to, or if the site doesn't prompt you, and you just have to kind of remember to go into it manually. It's kind of easy to forget and can kind of sort of be a pain. So yeah, that's kind of key management. And some practical world applications. We kind of touched on some of these already. Your TLS and SSL type encryption. So this is kind of like your web-based traffic encryption. This is where your HTTPS comes from. So this is kind of where that TLS handshake is, with where you do the cryptographic handshake. Basically, the server has its certificate to basically validate it is who it says it is. And the certificate is basically has multiple chain levels to it. So you gotta have the root certificate authority, which can then grant certificates to like the different domains and stuff. So basically, how your web browser verifies a certificate is it basically checks the certificate and the domain to basically make sure that they match up, to make sure that this is who the person says they are, and also make sure that the root certificate authority is actually valid. So this is typically, if you're in a home lab scenario, you will very frequently have your web browser yelling and screaming at you that the website you are trying to access is not secure or insecure, because it has a self-signed certificate, because the service you're using basically created its own root certificate authority certificate, which then it used to create its own certificate for the site itself. And that's of course a big red flag, because you don't have that third-party root certificate basically vouching and verifying that yes, this site is actually legitimate. So that is so basically that's why you get that message. So if you ever go to a website and you see that message like this website might be insecure and they might be trying to steal your data, typically it's really one of two main reasons. One reason is their certificate's just expired. They forgot to update it, which I guess common mistake maybe, but I think usually most of the certificates, like if you're using, I think Let's Encrypt, it generally kind of auto renews itself, so that theoretically shouldn't be an issue. But again, if you're kind of in a home lab scenario and you have to do that yourself, kind of easy to see how that could get mixed up. And then the other big one, which could be a red flag if you don't actually know the site you're accessing, is a self-signed certificate. Now, in a home lab scenario, it's really not that big of a deal. It's kind of an annoyance, but you can create your own certificate authority that you can then kind of import into all of your devices. Which I guess that's another thing that we should touch on too, is depending on who the root certificate authority is, your device still might not like it. So for instance, if you create say you're using pfSense and you create your own certificate authority on there to create certificates for your various internal web services that you host, like I do. If you go to one of those sites don't have a self-signed certificate, so in theory they should be fine, but they still get rejected by the web browser because the web browser doesn't recognize the root certificate authority as a valid certificate authority. So you basically have to take that root certificate and basically import it into your browsers, your devices, and whatnot, to basically let your devices know that this is in fact a trusted root certificate authority and you can trust them for the encryption. So that handshake thing is how kind of TLS works, and how you can then have that encrypted traffic between you and websites. Then, of course, as we kind of touched on with data at rest, database encryption is kind of another key one that you kind of need to have, especially if you're doing anything database related. You definitely should be encrypting things at the bare minimum. If you're storing things like passwords, you better not be storing those as plain text, or any kind of like payment details. But but just, encrypt the entire database. It makes your life a lot easier. So I think at this point we're kind of getting close on time here. We've been going for quite a bit. So I've been rambling for quite a while on all this encryption stuff, and I've probably lost a decent amount of people, if we're being honest, especially with that Diffie-Hellman stuff, all that kind of math and modulos and powers and things like that. Probably lost some people. So as a quick recap for everyone, if there is one thing to I guess a couple main takeaways for this episode, is basically just the importance of encryption and the various different types of encryption and the key role that kind of managing like keys actually is. Because in the case of symmetric key encryption, if your key gets out there, well, anything you encrypted with that key is basically toast at this point. It can be decrypted by whoever gets access to the key. Same thing with public and private keys. If you lose your private key, well, it's kind of the same thing if you lose your symmetric key. Anyone that has access to it can now decrypt whatever they want to and basically impersonate you. So kind of having ways to kind of swap between the keys or having expiry dates for your keys and having to renew them is one way to kind of help mitigate that. But the biggest takeaway that I want you to come away with this episode, if you don't remember anything else, is the importance of data at rest and encryption at rest and encryption in transit. Basically, what that boils down to is in order to make sure that your data is as secure as it can be, make sure when it is on your devices locally, in your databases, on your servers, whatever, it's encrypted there. And then whenever it's being transmitted from one device to another over the internet, you're using some sort of end-to-end encryption to make sure that that data is encrypted from the moment before it leaves your device. It gets encrypted, and it's encrypted the entire way until it gets to its destination. Only at that point, when it's at its destination, does it then get decrypted and then processed by whoever is on the other end. So those are the two very big takeaways that you need to take away from this episode in order to make sure that your data is secure: encryption at rest and encryption and transit. And speaking of encryption, that is the topic of our trivia question, so why don't we conclude with that? So our trivia question for the week is: AES, or the Advanced Encryption Standard, is a specification for the encryption of electronic data established by the United States National Institute of Standards and Technology, or NIST, in what year? So again, what year was AES established by NIST? If you said 2001, congratulations, you got this week's trivia question correct. And I hope you enjoyed this episode and got something out of it. And if you have anyone out there, or you know of anyone that is interested in kind of learning a little more about encryption, you definitely should send this episode over to them and just kind of share it around in general if you found it worthy. And if you did enjoy the episode, definitely be sure to like it, leave a rating on the podcast, subscribe, all that good stuff. And if you have any questions about this episode, or of any topics, comments, ideas, questions, or anything for future episodes, you can shoot me an email at contact@darkassassinsinc.com, or if you're on YouTube, you can just leave a comment down below. That works too. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, full nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.